So, have you ever stopped to think about how the raw, immense power you see crackling through those giant transmission lines somehow gets safely into your tiny phone charger? Well, the answer is a device that's both ridiculously simple and, frankly, genius. And today, we're going to pull back the curtain and see exactly how it works.
All right, here's our game plan. We're going to start with a massive real-world problem. Then we'll uncover this kind of secret partnership between two fundamental forces of nature. From there, we'll see how we can use that partnership to build a device that, as you'll see, powers just about everything in our modern lives. It's going to be fun.
So, first things first, let's really set the stage and understand the sheer scale of the challenge we're talking about.
To move all that electrical power across the country efficiently, we have to crank the voltage way, way up. We're talking hundreds of thousands of volts zipping through this huge network of power lines. That is an insane amount of power. Way too dangerous for any home, let alone any device you own. And that, right there, is the big question, isn't it? How on earth do we take that raw, deadly force from the grid and, well, tame it? How do we turn it into something safe enough to charge your phone? The solution is just incredibly elegant.
So the key isn't some complex electrical trick. It's all about using electricity's invisible best friend, magnetism. You see, these two forces are fundamentally unbreakably linked, and that connection, that's what makes everything we're about to talk about possible.
Okay, so here is clue number 1, and it comes from a basic rule of physics called Ampere's law. Now don't worry about all the math here. The big idea is super simple. Whenever you have an electric current flowing through a wire, it automatically creates an invisible magnetic field that just wraps right around it. You literally can't have one without the other. They're a package deal.
Now this is where it gets really interesting. On the left, you've got the cause. That's the initial magnetic push, the raw force that comes directly from the electric current. But on the right, you see the total effect. That's the magnetic field you get after it interacts with whatever material it's in. So we're not just looking at the push, we're looking at the final result.
So, if we've got this magnetic field just hanging around our electrical current, how do we actually grab it and put it to work? Well, we need to build something called a magnetic circuit. And our very first building block is the magnetic coil. It's a simple but powerful idea. By taking a wire and just wrapping it into a bunch of loops, we can take that weak, spread-out magnetic field and really concentrate it, making it much, much stronger and more focused.
Now, just like a regular circuit needs voltage to kind of push the electricity along, our magnetic circuit needs its own push. We call it magnetomotive force, or MMF for short. The easiest way to think about it is just as magnetic pressure. It's the force that gets that magnetic field up and moving where we want it to go.
And following that same logic, just like wires have resistance that fights the flow of electricity, different materials have what's called reluctance. They fight the flow of the magnetic field. But some materials, like iron, have super low reluctance. They're basically magnetic superhighways, letting that field travel through them with almost no opposition.
Okay, now we get to the really cool part. Let's see how all these pieces come together to pull off what feels like a magic trick, making an invisible leap from one circuit to a completely separate one. Right. Now take a look at this. You see those two big coils of wire? The most important thing to notice here is that they are not touching. At all. There are 0 wires connecting them. The only thing they share is that invisible magnetic field we've been building, which we can now guide from one coil to the other using our magnetic superhighway. This is where the magic happens. And here's how it plays out, step by step. First, we send an alternating current into coil number 1, which creates a magnetic field that's constantly changing, constantly pulsing. That pulsing field then travels through our iron core to the other side. And as that moving, changing field passes through the second coil, it does something incredible. It induces a brand new voltage. It creates electricity out of thin air in a totally separate circuit. So, with all those principles in our back pocket, we can finally put it all together and reveal the device that solves our huge high-voltage problem, the transformer. And this is it. This is the whole thing in its purest form. An ideal transformer is literally just what we built, a primary coil for the incoming power, a secondary coil for the outgoing power, and both of them wrapped around that shared magnetic core. That's it. It is just beautiful in its simplicity. Now, to really get how it works at its core, we first imagine a perfect transformer,
In this ideal world, we pretend no energy is wasted as heat, and we assume that 100% of the magnetic field from that first coil gets perfectly captured by the second one. It's a perfect, lossless transfer of energy.
And this is the secret sauce. Forget the formulas for a second, just look at the concept. It all comes down to the number of loops, or turns, of wire in each coil. Here's the trade-off. If your second coil has more turns, you get a higher voltage, but you get less current. If it has fewer turns, you get a lower voltage, but you get more current. We can literally trade voltage for current just by changing how many times we wrap a wire.
And voila! There's our solution. We use a step-up transformer at the power plant with lots of turns on the second coil to boost the voltage for that long trip across the country. Then, near your house, we use a step-down transformer with fewer turns on the second coil. It drops the voltage way down, making it safe for your outlets. Problem solved!
You know, here's the most amazing part. In this perfect ideal model, power is conserved. The total amount of energy you put in is the exact same amount you get out. No power is created or destroyed. It's just transformed from high voltage and low current to low voltage and high current.
So, let's zoom all the way back out and just appreciate how this one simple device is the unsung hero of our modern electrified world.
Seriously, once you know what to look for, you see them everywhere. The giant ones in power substations, the barrel-shaped ones on utility poles in your neighborhood, right down to the tiny ones hidden inside the power brick for your laptop. Every single one is performing that exact same invisible leap of induction.
It's really just a marvel, isn't it? A couple of coils of wire and a chunk of iron. That's it! Using the basic laws of electromagnetism to solve one of the biggest engineering puzzles of the modern age. It's just a perfect example of the power you can unlock when you understand these invisible forces.
And that really brings us to one last thought to leave you with. We just peeked behind the curtain at one invisible force that literally powers our entire world. It really makes you wonder, doesn't it? What other amazing principles are just hiding out there in plain sight, waiting for us to understand them and build the next piece of technology that changes everything?